So hello, today's topic is about growth and decay. So let's define what is growth and decay in this context by differential equation. So the law of exponential change states that the rate of change of the amount of substance, okay, is proportional to the present amount of the substance, okay. So given that we have d of differential equation, okay, dA over dt, okay, the rate of change of the substance as time passes, or yeah, as time passes, is equal to the k. K is the constant, proportionality constant, times a, the amount of substance at any time t. Okay, if we're going to solve this, get the general solution of this uh, differential equation, that will be a equals c e raised to k t. Okay, so let's use this general solution to solve some real life problems. So for this example, we have a sample 1. Okay, a certain population of bacteria is known to grow at a rate proportional to the amount present in a culture that provides plentiful food and space. Initially, there are 450 bacteria. Okay, initially. So, and after 7 hours, 900 bacteria are observed in the culture. So, let's determine the approximate number of bacteria that will be present in a culture after 20 hours. Analyzing the problem, we have a given here 450 bacteria, okay, initially. So we can say that at time 0, okay, the initial bacteria, okay, a sub 0 is 450. Okay, and then after 7 hours, a sub 7, okay, after 7 hours, there are 900 bacteria present in the culture. Now, we need to find the number of bacteria after 20 hours. So that will be a sub 20. We need to find this. Okay? So in order to get the answer, okay, we'll be using this general solution. Okay, let's copy this general solution. So at the beginning, at time 0, the amount of bacteria is 450. Okay, 450. So if we're going to substitute this these values, okay, so this will become 450 equals c times e raised to k, the proportionality, okay, times 0. Okay, we will get c here, which is equal to 450. Okay, now if we're going to uh, substitute the value of c in the preceding equation, we now have a, so this will become a equals 450, okay, e raised to k t. Next, let's find, okay, so let's now find the value for k, the proportionality. So we'll be using this given, okay, at time, so at time 7, okay, the amount of bacteria, okay, is 900. Okay, it's 900. Now let's substitute those value, okay, so that we could get the value of k. So this time we will be using this equation. Okay, so let's substitute. So we have 900 here equals 450. Wait, okay, times e raised to k t, and rt is 7. If we're going to evaluate that, you will get k here equals ln of 2 over 7. That will be the value of k. And this general, or this preceding equation will become a equals 450 e raised to ln 2 over 7 times t. Okay. This will be our new formula. Now, in order for us to get the value, okay, of this a sub 20, the amount of bacteria after 20 hours, so we will be using this equation, okay, this new equation or new formula. So let's say we have at time 20, what will be the amount of the number of bacteria here, okay. So let me copy this first. Okay. So this time we just need to substitute all the values here, okay. So I'll revise this. So this will become a sub 20, and our t will become 20 also. If we're going to evaluate this, the answer will be a sub 20 equals 300, or 3000 rather, 3260.6051. But take note, okay, it is bacteria, so there should be it should be whole number, okay, it should be whole number approximately. So the answer here will be 3261. Okay, round up. So that will be the answer here at example number 1. Okay. Next, another example. So let's say, okay, we have a population here. The population of a certain country is known to increase at a rate proportional to the number of people presently living in the country. So if after 4 years the population has doubled, and after 3 years the population is 20,000, find the number of the people initially living in the country. Okay. Let us first analyze the given. So here we have after 4 years, so a sub 4, okay, the population has doubled, so meaning the initial so this means that the initial here, the initial population is doubled, okay, times 2, so 2 times a sub 0, and then after 3 years, so that will be a sub 3, the population is equal to 20,000. Okay, 20,000. So okay, let's proceed with its general solution. Let's see. So in this case, at time 0, we have, okay, at time 0, no, our population, okay, is equivalent to a sub 0, so let's set it like that, okay. And then this will give us here a, okay, so this equation, this general solution rather, will now become this one, okay, because here, okay, if we're going to calculate these, our C is basically equal to a sub 0, okay, so this will be our new equation or formula to solve to be used, okay, in this example. Now it said that at time 4, oh yeah, at year 4, okay, at year 4, years, okay, our population here is doubled, okay, so the initial population is doubled, okay, so using this equation, so this will become now so this A will become A sub 4, and that A sub 4 is 2A sub 0, right? And then this t value will be replaced by 4, indicating 4 years. And if we simplify this, we could get the value for k, the proportionality constant, and that is ln of 2. ln of 2. Now, our new equation or formula here will be a equals a sub 0 times e raised to ln of 2 times t, or you can say, yeah, we can say that we have t ln of 2. Okay. This will be our new formula here. Next, so now at year 3, the population here a sub 3 is equal to 20,000. So let's use this, or let's plug this given here in our recent formula. So if we plug it here, so this will become 20,000, okay, equals a sub 0 e raised to t, that is 3 years, times the proportionality constant, that is ln of 2. Okay, and if you're going to simplify this, we could now get the value of a sub 0, the initial population, and that is equal to, okay, that is equal to this one. Okay. So we have here 2,500. So this will be the initial population. Okay. And yeah, this is the final answer. Okay, so this is the application of the differential equation